Hello everyone, my name is Alnur Elbarer and I'm an IoT and Cloud Field Apps Engineer at STMicroelectronics. Today, I'll be guiding you through our Getting Started with AWS Greengrass Lite on STM32MP1 workshop. This workshop walks you through configuring the STM32MP135 Discovery Kit as a BLE to AWS IoT Gateway using AWS IoT Greengrass Lite. At a high level, AWS IoT Greengrass lets you process data, run code, and communicate with AWS services directly on the edge device, even when offline. It also supports remote device management and component deployment, allowing you to monitor, update, and control devices from the cloud. In this session, we'll be using Greengrass Lite, a lightweight version designed for resource-constrained Linux systems. It retains core features like secure messaging and modular components while enabling more cost-effective, low-power hardware options. Our hardware platform is the STM32MP1, a Linux-capable microprocessor that delivers a strong balance of performance, power efficiency, and security, making it an ideal fit for running Greengrass Lite at the edge. Now, let me show you an overall architecture of what we hope to accomplish today. On the bottom, we have our ST-eval Proteus industrial sensor nodes, delivering sensor data over Bluetooth. That Bluetooth data is captured by our STM32MP1 board and then communicated via Wi-Fi and IoT MQTT protocol to AWS IoT Core, where it can then be processed by other downstream AWS services. What you see on the screen now is the README for the repository that accompanies this workshop. If at any point you'd like to refer back to the documentation, please do so, as it's linked in the video description. There are several steps that we'll need to accomplish for today's workshop. On a high level, we'll be flashing the MP1 with the OpenSTLinux starter image. Next, we'll connect the MP1 to Wi-Fi, followed by installing Greengrass Lite on the MP1 and provisioning it as a Greengrass core. And lastly, we'll deploy a BLE Gateway component to the MP1, which enables us to connect and read sensor data from our ST-eval Proteus board. For today's workshop, there are several hardware requirements and software prerequisites that we must meet. For cabling, we need a USB-A to USB-C data cable, USB-C power cable, USB-A to micro USB cable. We'll need the ST-eval Proteus 1 board, which can be purchased from the link provided in the README documentation. And of course, we'll need the STM32MP135 Discovery Kit, again, which can be purchased from the link in the description. In terms of software prerequisites, you'll need to install STM32Cube Programmer. You'll need to download the STM32MP135 starter package. You'll need to have Git Bash installed in order to run shell scripts in a Windows environment. You'll need an AWS account and AWS CLI installed. In addition, you'll have to make sure that AWS CLI is configured with your AWS account. Lastly, there are 3 Git repositories that must be cloned, 2 of which are linked as submodules to the repository included in the video description. To clone all 3 repositories, follow the GitHub repository link in the video description, scroll to the Git submodules section, and use this command to clone the repository with all the included submodules. If you've already cloned the repository without including submodules, you can use this git submodule update init recursive to then clone all the submodules that are included. The included submodules are the Greengrass Lite setup repository. This repository is responsible for installing and provisioning Greengrass Lite on your STM32MP1, and the BLE Gateway setup repository, which holds the BLE Gateway component which will be deployed to your STM32MP1. The first step for today's workshop is to flash the OpenSTLinux starter package image. The link to download the image can be found in the README. Just select Get Latest here. Off camera, I've already downloaded the image. to my desktop. Next, what we'll do is extract it. Okay, great. Next, we'll need to install the STM32 Programmer dependencies. This allows us to connect to our board over USB and DFU mode. For Linux, you'll have to install libusb version 1.0.0 and then copy dev rules from your QProgrammer path to your udev rules. On Windows, you'll just run the STM32 bootloader.bat script held at the STM32 QProgrammer install path, drivers, and then DFU driver. My QProgrammer install path is Windows C, Program Files, STMicroelectronics, STM32Cube, STM32Cube Programmer, drivers, and then DFU driver. In this directory, I'll right-click, open in Terminal, and then run the STM32 bootloader script. And that's all. Now we're all ready to connect our board to the PC. First, we'll have to set the boot switches to DFU mode. To do so, we'll set them all to open as imaged here. Next, we'll connect our USB-C power cable to CN12 as imaged here. And lastly, we'll connect our USB-C data cable to CN7 as imaged here. Feel free to pause the video while you connect your board. Next, with our board connected, we can open up STM32 QProgrammer. We'll change the connection mode to USB, and if you don't see a serial number populated here, just hit the refresh button. Now, we'll click Connect. Next, we'll open the file that we hope to flash to the board. I know that my file was extracted to my desktop, so I'll open up the folder that was extracted, then go to Images, STM32MP1, Flash Layout, ST Image Weston, opt, and then I'll look for the MP135 image. Flash Layout, SD card, STM32MP135F, dkopt.tsv. Next, we'll set the binaries path. We'll hit Browse, and it should be in the same folder that we extracted earlier, Images, and then STM32MP1, and select folder. Now, we can click Download. This download takes roughly 5 minutes, so feel free to pause the video here while you wait for your download to complete. Once you see flashing service completed successfully, you can click OK, disconnect from the board, and then we'll want to reset our boot switches as imaged here. One will be closed, 2 will be open, 3 will be closed, and then 4 will be open. You can now power cycle the board with the black reset button imaged here and boot into the image on the SD card. It takes a few minutes for the OpenSTLinux image to boot up completely, so feel free to pause the video here while you wait for the image to fully boot. Once you see a date and time in the bottom right-hand corner of your screen, you know that the board is fully booted, and we've successfully flashed the OpenSTLinux starter package image to our discovery kit. Next, we'll connect our board to Wi-Fi. To ensure that our board is fully booted, we'll just want to verify again that a date and time is imaged here in the bottom of your screen. Next, we can disconnect the USB-C data cable that we plugged in earlier and connect a micro USB data cable to the ST-Link port as imaged here. Now, if we navigate to the repository that we downloaded for this workshop, you'll see two configure Wi-Fi scripts, one PowerShell script for Windows and one shell script for Linux. Open the script in a text editor that corresponds with your operating system and update the SSID and password to what matches your environment. Save the script and close it. You can right-click in the window and open this directory in Terminal. From here, we'll just run the configure Wi-Fi script. This script will open a serial port connected to the ST-Link, send the commands required to configure the Wi-Fi onboard the discovery kit with the password that you just entered into the text file, and after it sends the commands, it will ping Google and verify that the connectivity is set up. Assuming everything went okay, you should see 4 successful pings to 8.8.8.8, or in other words, google.com. Now we've successfully connected our STM32MP1 discovery kit to Wi-Fi. Next, we'll want to take note of the IP address for our board. To do so, you'll want to select the Net Data Perf Monitor button on the touchscreen. This will open an application that displays the IP address as a URL. Next, we'll want to install AWS IoT Greengrass Lite and provision our STM32MP1 board as a Greengrass core device. To do so, we'll open the repository accompanying the workshop. Assuming we've already downloaded our submodules, we should see STM32MP1 AWS IoT Greengrass Nucleus Lite. If we haven't, we can use this git submodule update init recursive command in this window. Otherwise, we'll navigate into this folder, and then we'll see a config.json file. We can right-click and edit in Notepad. There are 3 parameters that we'll have to update here. One is the board IP that we noted earlier. Next, we'll have to create a thing name. This will be the thing name that Next, we'll enter our desired thing name, and desired thing group name. And save the file. Now, we can open terminal in this directory by right-clicking in the folder. Because I'm in a Windows environment, I'll need to use git bash to run the script. By default, git bash is installed at C, Program Files, Git, and then the bin file for the shexe is bin.shexe. Next, we'll just have the execute script and click enter. This script first checks that it can SSH to the IP address that you provided in the config file. Then it creates all the policies and resources required to provision your STM32MP135 board as a Greengrass IoT core. Next, it creates the certificates required to register your board, copies all the necessary files over to the MP1 board, installs a few dependencies, and then begins the install for Greengrass Lite. This section of the install does take some time, so I'll be speeding it up for the video. Feel free to pause here while you wait for your install to fully complete. Once you see all scripts executed successfully in the terminal window, your board is now registered as an AWS IoT Greengrass core. To verify this, we can log into the AWS IoT console. In the GUI, select Greengrass Devices, Core Devices, and you may need to refresh, but you'll see your demo core listed there. You'll notice that the core is running AWS Nucleus Lite 2.0.0. If you have any issues with this process, please refer back to the documentation, as there's a full README for this section provided here. Next, we'll deploy our BLE Gateway component to our STM32MP1 Greengrass core. This final step shows the power of AWS Greengrass. By deploying the BLE Gateway as a Greengrass component, you're turning your STM32MP1 into a working BLE edge device, without writing setup code or docs yourself. Greengrass makes it possible to package, deploy, and manage this functionality securely, remotely, and at scale. The first step is unboxing the ST-Eval Proteus industrial sensor node. The board comes pre-imaged with compatible firmware, so there's no need to flash any additional images. You'll just connect the board with your USB-A to micro USB cable as imaged here. The board is delivered with a battery and packaging, so if you'd like to watch a video to set up your board as a battery-powered node, you can click this video link here. Next, we'll want to update the config.json for the BLE Gateway deployment. To do so, we'll navigate into the repository for the workshop, and then into the Greengrass Lite BLE Gateway Proteus submodule. Here, you'll find a file called config.json. We'll select it, right-click, and then hit Edit in Notepad. There are a few parameters here that we'll have to update to match our environment. Firstly, the target group should match the group name that we created with our demo core. Which for my setup was demo core group. The region must match the AWS region that you created your IoT Greengrass core in. Since this is the first iteration of our component deployment, the version will remain 1.0.0, and the component name can remain com.example.ble-gateway. We'll save this file and close it. Next, we'll want to open a terminal window in this directory by right-clicking and select Open in Terminal. Again, we'll want to use git bash. So to do so, we'll enter the path but this time we'll be using it for a script called deploy.sh. Enter. This script will create the S3 bucket if not already existing, upload the artifacts to the S3 bucket for the deployment, upload the recipe for the deployment, and then create the deployment for our target group. If we navigate into AWS IoT, and then Greengrass Devices, Deployments, we'll see a deployment that will have been created just now. We can also go under Core Devices, and then select our core, and then Deployments to see the status of the deployment. Feel free to pause the video here, as this deployment does take some time. I'll fast forward and continue to refresh for video purposes. Great. As you can see, the status on the device has switched to succeeded. Now, if we navigate to the MQTT test client and subscribe to Hash, which subscribes to all the topics available on the test client, and hit subscribe, you'll see various data being published on several topics. You may have to power cycle your Proteus board in order to restart the publishing of sensor data. If you have any trouble with the BLE Gateway deployment, please refer back to the README, as there's a full README provided here for this section.